Okay, so we're going to be looking at what happens to our base if we let the number of compounding periods get very large. So what I have here is that 1 plus our rate divided by the number of compounding periods, and then we're going to take this to the power of the number of compounding periods. This is our base in our exponential function. What you see here is with compounding once a year, that gave us a base of 1.1 or a 10% return. If we let n be equal to 2, we see that our base is now 1.1025, which means that we're making 10.25% per year. So that interest that we got out was going up. If we let it be equal to 52, that was the last example that we looked at, we get this base of 1.105, which means that we're making 10.5% per year. Okay, so that because we're making interest on our interest, this is going up. All right, and so the question is, what's going to happen if we let this number of compounding periods get bigger and bigger and bigger? Okay, and so what I'd like you to do is first make a guess as to whether this will, blow up. Is it going to be bigger than 4? Is it going to be bigger than 5? Or do you think it'll sort of level out? And then I'm going to click this and it's going to play to see if you watch this number, it'll show you how big that base gets. Okay. We can see that as this number of compounding periods in a year goes up, that number is rising, but it's not like shooting out of control. In fact, it seems to be getting close to some value, right? It seems like it's kind of stabilizing. Whoops. And in fact, there is an upper bound on how big this can get. There's a number E, where if we take E to the 0.1, this tells us that biggest value that we're going to approach as n gets close to infinity. The number E is a special number, but it's just a number. It's approximately equal to 2.71828. So let's take a look. This is what's going to be called continuous growth. If we have what's called continuous compounding, we can model it as P naught e to the RT, where P naught is going to be our initial value, R is going to be our growth rate, and T is our time. So in our example, the limit on how much extra bang we can get from compounding, basically all interest goes back into the principal, is going to be 10,000 e to the 0.1 t. And we can see after 30 years, this is 10,000 e to the 0.1 times 30, or 10,000 e to the 3. So there is, on your calculator, there's a specific button for E. E is the number 2.71828. Like pi, it goes on forever. It's irrational. This number gets used super frequently in math and science. And you'll see in calculus that it's got some special properties. Okay. So if we have this continuous compounding, in 30 years, our investment would have made this sort of upper bound amount of $200,855. Okay, cool. But the often much more important than how frequently we're compounding is just going to be the growth rate. So if you have a difference between like a 10% rate and 7% rate, the 10% one is almost always going to be the better one. Great.